In this lecture, we talk about Frobenius endomorphism. So recall the binomial theorem. So expansion of a plus b to the power of p is given as summa p choose k, a to the power of k, b to the power of p minus k. So if you are working in a field of order p, so this is a finite field and it has order p, so then all these coefficients except 1, they are all divisible by p. So these are divisible by p. So in this finite field, all these coefficients will vanish except 1. So you have this equality here. So this is important because now we can use a homomorphism from fp to fp, where you take an element x here and it gets mapped to x to the p. And you can check the product obviously will be like this, and the sum will be like this from here. So in particular, if you have a rational function like this with coefficients in your field of order p, then if you take this rational function, raise it to p, you can write it as fx1p all the way to xn p. And that is because you can use this result and you can use this result, or you can use multinomial theorem. So you have taken care of both the multiplication and addition. So now we talk about Frobenius endomorphism for a elliptic curve. So Frobenius endomorphism for an elliptic curve E over FQ is this map. So you talk about in projective coordinates, this gets mapped to xq, yq, zq. Now we are talking about any finite field FQ rather than just a field FP where P is prime. So this is just a finite field and say of order Q. So finite field of order Q. So say you're given elliptic curve like this in its projective form, y square z is x cube plus ax c square plus bz cube. Then we can raise both sides to the power of q, and then you will get y. You just rearrange this. You get yq square zq and then xqq plus this and then this. So again we are just using this result that a is equal to a to the power of q, b is equal to b to the power of q in this fq. So again this elliptic curve is over this fq because the coefficients are in fq, but the points, you recall that points we always describe over the closure. So this bar means it's the closure of this field. So this is just this in fq. So again, so if you start with these points in the closure of fq, then these corresponding points will also lie in the closure of fq. So we have just proven if this lies in the closure of fq, then the corresponding, if you raise to the power of q, they will also lie in the closure of fq. So you have a proper map of two elliptic curves via Frobenius endomorphism. Now we have to check that if we are saying it's an endomorphism of elliptic curve, so it has to preserve the group law. So the group law is obviously preserved because the group law, this addition, and this addition is defined via certain rational formulas. So we define addition via the chord tangent process, which was made algebraic. So this group law is defined via rational functions, and we have seen these rational functions from right here that they do not change if you take powers of q. So they do not change if you take exponent q. So they will again become something like this. So the group law is preserved. Only thing we need to remember is, although we have been able to construct this isogeny in one direction, there is no isogeny in the reverse direction, because this is a rational map. As you can see, x, y, z is taken to x to the power of q, y to the power of q, z to the power of q. So these are all rational functions. xq, yq and zq are rational functions. So these are rational functions, but there is no inverse of these functions. So there is no inverse rational function for Frobenius map. So there is no function like this which will be rational. Obviously, to go back, you have to take x to the power of 1 by q and say y to the power of 1 by q and say z to the power of 1 by q to have an inverse map. But this is not a rational map. See the powers. So this is not a rational map. So there is no inverse rational function for Frobenius map. So therefore there is no isogeny in the opposite direction.